In this video, I will discuss a JEE Advanced PYQ based on the topics simple harmonic motion and conservation of linear momentum. Simple harmonic motion is a to and fro motion about a mean position. Let me consider this simple system. A block of mass n connected to a spring constant K, which is fixed at one end, and the whole thing is lying on a horizontal surface. This is the relaxed position of the spring. So from this relaxed position, I take this mass to a distance of E and leave it. So the mass will start moving towards this mean position because the stretched spring will try to pull it back. So it will come to the mean position. So the velocity will increase from initial velocity of 0. And once it reaches this position, the velocity will decrease. Because after it reaches this position, the spring will compress and try to push it back to the mean position. So the velocity will keep on decreasing until it becomes 0 here. It starts with 0 velocity because it's released from here, and the velocity of this mean position is maximum. And once it turns back, the velocity will keep on increasing because the compression will try to push it. The velocity will keep on increasing until this point. Again, it becomes Vm, and not stop here because the velocity is there. So it will try to go further. Here, at this point, the spring is getting stretched, so it will try to pull it back. So velocity will keep on decreasing until the turning point. So again, the velocity here is again 0. So this motion will keep on repeating. And this motion is called simple harmonic motion, or SHM. Actually, it's going from here to here. The velocity is towards left, so it should be minus. X direction I am choosing as towards right. The direction of positive x-axis. So it's going this way. The velocity is positive. So the x displacement of this motion will look like this: A sine omega t plus phi. There are a few interesting things to note about this motion. The kinetic energy of this motion, which is half m v square, because there is spring is massless. So kinetic energy here is 0 because velocity is 0. And the kinetic energy at the main position is maximum because velocity is maximum, and kinetic energy again here is 0. And when it comes again, the kinetic energy will be maximum and keep on repeating. The potential energy stored in the system is the energy stored in the spring, which is half k x square. Potential energy stored in the spring is half k x square, where x is the extension of the spring or compression of the spring. So at this point, the spring has stretched maximum. So potential energy stored in the spring is half k, where k is the spring constant, and the extension, the amplitude. This is the amplitude of the motion. So half k x square. Here, potential energy stored in the spring is 0 because extension is 0. This extension from the relaxed position. Here the spring is getting compressed by an amount A. So potential energy here is again half k A square. So you can note that when the kinetic is maximum, potential is minimum. When kinetic is minimum, potential is maximum. Here again kinetic is 0, potential is maximum. So the total energy of the system, which is kinetic energy plus potential energy, there is no other form of energy, and there is no dissipation because this surface is smooth, frictionless. There is no dissipation. So this is constant. So this total energy is same at all points. I can find the total energy here or here or here, anywhere, and I can get this value. But there are two convenient points at which I can find the total energy. One point is this mean position. So there the energy is maximum, and the potential energy is 0 because the extension is 0. So this is the main position. I can also find the total energy at one more convenient point, which is the extreme position. At the extreme position, kinetic energy is 0 because it's a turning point, the velocity is 0. But the potential stored in the spring is maximum because half k extension square, this k is spring constant, this k is kinetic energy, and the extension, the extreme position is amplitude of the oscillation. This is the extreme point, extreme position. So to find the total energy, I can use these two convenient points to find the total energy. This k is nothing but half capital M V square, Vm square. Vm is the velocity at this point. So one thing to notice is, if total energy is known, then I can find maximum velocity of the motion and also the amplitude of the motion. This is known, it's half m v square. M and k are known because the system is known. So Vmax is known. From here I can get the amplitude of the motion because spring constant is known. There is one more basic concept that's required for this question, which is conservation of linear momentum. This block is oscillating like this, and I place a small mass, small m, on top of this one. Initially, the small m is at rest. I just drop it on this one. So as soon as I drop it here, the velocity of the combined mass will change a little bit, and the combined mass will keep on oscillating. And one more condition is, this m sticks to this capital M as soon as it's placed on this one. That's the given condition. So the change velocity of this combined mass we can find by conservation of momentum. Initial momentum equal to final momentum. Initial momentum is the mass, the initial mass, which is just the m, will have some velocity. And the final momentum, the final mass is the combined mass. Both of them will move together into some final velocity, Vf. So since the system is known, m is known, small m is known, so and v is also known. Because I know the velocity at a particular position, at that point I keep placing this mass in. So the change velocity of this combined mass I can find out from this relation. So from this I can find Vf. So with this basic understanding, we can solve this JEE advanced question. This is the question. A block with mass capital M is connected by a massless spring with stiffness constant K to a rigid wall and moves without friction on a horizontal surface. The block oscillates with small amplitude A about an equivalent position x0. Consider two cases: one, when the block is at x0, and two, when the block is at x0 plus A. In both cases, a particle of mass small m less than capital M is softly placed on the block after which they stick on each other. Which of the following statements are true about the motion after the mass m is placed on the mass capital M? Option A, the amplitude of the oscillation in the first case changes by a factor square root of m by m plus n, whereas in the second case it remains unchanged. Option B, the final time period of the oscillation in both cases is same. Option C, total energy decreases in both cases. Option D, instantaneous speed at x0 of the combined masses decreases in both the cases. So it's multiple choice question, more than one is correct. So you have to check all these options individually. You can pause and run this question. So initially the mass capital M attached to a spring or spring constant K, and this on a horizontal surface is oscillating. Okay, and first case, the small m is attached to capital M at x0. This is the initial position, x0. Okay, So in case 1, small m is attached at this position. So this is case 1. And case 2, when the mass at the extreme position at a distance of a, amplitude of the oscillation, the mass is placed here. So initially, let the velocity of this mass when it is oscillating here, let it be Vm naught. Let me call this case 0, the initial one. Okay, so in the first case, the velocity of this mean position is the maximum velocity that I can find out by conservation of linear momentum. So momentum of the system before this mass is placed in the first case is m into Vm, the maximum velocity at this point. In the 0 case, that should be equal to the combined mass m plus m into the maximum velocity because it's the mean position, the velocity maximum in the first case. So in the maximum velocity in the first case, Vm1 is m by m plus m into Vm naught. So the velocity, the maximum velocity in the first case is reduced. In the second case, the mass is placed in the extreme position. When this capital M is in the extreme position, the velocity is 0. So the initial momentum of the system is 0 because it's m into 0. That's equal to the final momentum, which is m plus m into the velocity of the turning point in the second case. Actually, it's V minimum in the second, which is 0. So in the second case, there is no change in the velocity. Here, as soon as the mass is placed on this one, there is a change in velocity. Velocity is decreasing a little bit by a factor m by m plus m plus m. In the second case, there is no change in the velocity. So the amplitude in the second case will not change because this is the initial condition. I will keep on maintaining that amplitude. But here the amplitude will change because the energy has decreased. So it will go somewhere here and turn back. So those things we can find out. To find the amplitude, if I know energy of the system, I can get the amplitude here. So energy of the system I can find by 2 ways. So total energy of the system in the first case, where m is placed on this capital M when it's the mean position, it's half m V max square velocity at this point because the potential energy at this point is 0, and it's also equal to the extreme position half k E1 square. Amplitude has changed, would have changed in general. Spring constant is same spring. Okay, so this will give me half can get cancelled. Vm1 from this thing I can get as m by, sorry, I made a mistake here. This should be m plus m because in the first case the mass is m plus m. First case the total mass which is oscillating is m plus m, so conducting of the system is the total mass into that velocity. So this will be Vm square. So this will be this square Vm naught. Vm in the first case, this one, it's reduced by a factor n by m plus m into Vm naught. That's equal to half a square cancelled, so just k into V1 square. So and This amplitude I can get in terms of, so total energy in the first case, zero case is half m, only capital M is oscillating in the first zero case, half m Vm naught square, which is equal to half k E square. Okay, so from the second element Vm naught. So this thing will become m square by m plus m into Vm naught square. So Vm naught square I can get from here. So this will give me Vm naught as k by m square root into V. So this will be, if we use it here, Vm naught square will be k by m A square equal to k into k1 square. So m and the square will get cancelled. So k a1 square. So k will get cancelled. So a1 is amplitude in the first case, which is different from the amplitude in the original case by a factor. Its square, so I will take the square root. So amplitude in the first case is changed or decreased by an amount, square root of m by m plus n. So option, the amplitude in the first case is changed by a factor m by m plus m, which is true. Second case is unchanged. Second case amplitude will not change because in the second case, this m is placed here. So the initial condition is this much amplitude. So the amplitude will be maintained. So amplitude in the second case is same as the first case. Amplitude will not change the second case. Because amplitude is decided with the initial position or the initial extreme position. So this mass is placed in the extreme position. So since this amplitude is fixed, it will maintain the same amplitude. So option A is true. Amplitude oscillating in the first case changes by a factor square root of m by m plus m. Second case remains unchanged. Option B, final time period of oscillation is same in both the cases. For a simple harmonic motion, k equal to m omega square is valid. For SHM, the spring constant k equal to the mass of the system into omega square. Okay, so in the first case, k is the same k and the masses of the system, let me call this case 1. Okay, mass of the system is m plus m omega 1 square. In the second case, spring constant is same spring k and the mass is again the combined mass into omega 2 square. So from this, omega 1 and omega 2 are same. And time period t is 2 pi by omega. So this means t1 equal to t2. So in the second case and the first case, the time it takes to complete one, here the amplitude is reduced, here the amplitude is same, but the amount of time it takes to make one oscillation is same in both the cases. But the original omega naught, zero case. So this time period is different. T naught equal to 2 pi by omega naught. Omega naught is different from omega 1 and omega 2 because the mass has changed. So T1 equal to T2, but it's not equal to T naught. But the option B is saying time period in case 1 and 2 is same. Final time of oscillation both the cases. The case he is referring to is this 1 and 2, not the initial one. So option B is also true. Option C, total energy decrease in both the cases. Total energy I can get by multiple two ways or two convenient ways. One is the energy at the extreme position. Total energy is sum of kinetic plus potential energy of the system. Energy of the system is half m plus n v square and potential is half k x square. But if you take the extreme position, at extreme position, kinetic energy is 0. This I can calculate at any point. So one convenient point is the extreme position. So I calculate the extreme position. So in the first case, spring is same, half k and a1 square. In the second case, the total energy of the system at the extreme position is the energy stored in the spring because kinetic energy is 0. It's half k a2 square and a2 is same as the initial a. This is half k a square. So which is equal to the total energy in the 0th case, the original one. But a1 is less than a that we have. That is the first option. That we check the first option. So this is less than half k a square because a1 is less than a by a factor. That's the first option that we check. I'm going to in the first case changes the factor root of m by m plus n. So it has decreased. So a1 is less than the original a. So total energy in the first case is less than total energy in this initial case, 0th case. So the energy has decreased in first case, not in the second case. So option C is the total energy decrease in both the cases. So option C is wrong. And one more interesting note is we can have an understanding why the energy has decreased in the first case. In the first case, I am placing this mass when the capital M is at the mean position. So when I am placing it, the thing is moving. So when the swan with zero velocity is placed on this one, there will be some relative motion between for a very small time before they stick to each other. So there will be relative sliding. So there will be a friction. So there will be a dissipation or heat energy. So the decrease in this T1, which is less than T0 because of this dissipation. In the second case, the swan is placed at the extreme position where it's not moving. So this also rest, this also rest. So just placing and then they both of them move together without any friction or the initial friction. So here there is no heat energy produced. This is another way of understanding this result. Option 4. Speed at the mean position x0 of the combined mass decrease in both the cases. So total energy I can get also from the condition the mean position. Total energy equal to half m v mean position velocity. Actually, the same is m plus m. In the first case, the mass that's moving is the combined mass m plus m v m1 square. So this is total energy in the first case. Similar total in the second case, half m plus m v m2 square. Okay, so to get this velocity so in the 0th case, I can write this as half m v m0 square. Because in the 0th case, the mass that's moving is only the capital M. That will give me Vm2 Same thing, m by n plus m, which is a fraction into Vm naught. So in both the cases, the maximum velocity, that's the velocity of the mean position, has decreased by a factor square root of m by n plus m. So option 4 is also true. Instantly speed at the mean position of the combined mass decreases in both the cases. So D is true, E is true, B is true, C is false. That is the correct answer. Only C is false. So this is what I explained here. K0, mass capitals oscillating in spring K. This is the first zeroth case, the original situation. So total energy of the system is, I can take this total energy, this mean position. So the kinetic energy is, potential stored in spring is 0. So only the kinetic energy will be there. It's half m Vm naught square, which is same as the energy stored in the extreme position, which is half k E square. Total energy I can get in two convenient positions. One is at the mean position, where the position is 0. Only the kinetic energy is there, which is half m V square. V is Vm naught square. And at the extreme position, kinetic energy is 0 because the turning point velocity is 0. So only the potential of the spring will be there. So it's half k E square. Case 1 small m attached to m at x naught. This position, mean position. Case 2 small m attached to m at the extreme position at x naught plus a. That is this position. There is ambient obsession. So to solve this question, we are using momentum conservation and energy conservation. So case 1, after small m is attached to capital M, velocity of the combined mass, let it be Vm1, because it's attached at the mean position. At the mean position, the velocity will be maximum, so that velocity will be Vm in the first case. So initial momentum is only this one, m into Vm naught. Final momentum is combined mass, m plus n, in the common velocity is Vm1. Total in the first case is kinetic energy in the mean position. At the mean position, potential is 0, so only kinetic energy will be there. It's half m plus m into Vm1 square, and Vm1 I can get from here as m by m plus m into Vm1. So using that, Vm0 square, and Vm0, Vm1, this I just rewritten here. 1m I have cancelled, 1 I have kept here. Okay, so this is total energy in the, okay, total energy in the first case is this one, half m Vm0 square. It will be a fraction. So this is less than this one by this factor out, which is less than 1. So total energy in the first case is less than total energy in the original case, and this is because the heating, because the friction here. So in this first case, there is a friction because I'm placing this small m when this mass is moving. So before it starts moving together, for that very short time, there will be a sliding motion, which will create some friction, and there will be some dissipation. That's why the total energy in the first case is less than the energy in the original case. Total energy in the second case, I can find by using the potential energy at the extreme position. This is at a convenient point. It's half k A square. And in the second case, the amplitude does not change because I'm placing this mass when the mass has reached the extreme position. So since this is the initial condition now, this amplitude will not change from this original value. We'll maintain that. So this is same as the total in the first case. So in this second case, there is no sliding motion here because I'm just placing this at velocity 0 when this thing is at rest, momentary rest. So there is no sliding force here. So option C, which says total energy decrease in both the cases is false. Total energy decrease only in this case because of friction. So C is false. Total energy in the first case is potential energy at the extreme position, which is half K A1 star. Also, the total in the first case can be found by using kinetic energy at the mean position, because at the mean position, potential energy is 0. It's half m plus m the combined mass of the Vm1 square. And this new velocity we have found here it is different from this old velocity by a factor m by m plus n. So using that, we'll get this one. And then half Vm naught square I can eliminate from here. This is the zeroth case. So in the zeroth case, half m v naught square equal to half k a square. This one is zeroth case. So this I can replace as half k a square into a fraction. So amplitude in the for these two are equal because total energy I have found in the first case by two ways. So these two should be equal. So from this I'll get A as A reduced by a factor square root of m by m plus n. So option A is true. Option A says in the first case the amplitude is decreased by a factor, this one. Second case is unchanged because I'm placing this thing at this extreme position, so with this thing will keep on continuing. So option A is true. And k equal to m omega square, m is the mass of the system. So in the first case the mass is m plus n. Second case also the mass is m plus n. Spring constant is same. So omega 1, omega 2 should be same. And time period is 2 pi by omega. Since omega is same, time period is also same. So B is true. Option B says the time period of oscillation in case 1 and case 2 is same, which is true. Momentum conservation in the first case, before placing the mass, the velocity is momentum is m into Vm naught. After placing the mass, the momentum, the relative velocity will be Vm1, and the combined mass it's moving with velocity source. So from this we can get Vm1 as m by m plus m, which is a fraction into Vm naught. So Vm1 is less than Vm1. Total in the second case half k a square, which is same as energy in the zeroth case. And the total in the second case I can get right as the kinetic in the mean position, which is half m plus n Vm square. And total in the zeroth case, again I can write as a kinetic is the mean position. So again Vm2 is Vm naught is the factor, which is a fraction m by m plus n square root. So Vm2 is also less than Vm1. So in both the cases the velocity, maximum velocity, which is the mean position, has decreased. So option D is true. Decrease in both the cases. So the correct options are A, B and D. C is false. It's somewhat lengthy question, but the concepts are simple. It's basically conservation of energy and conservation of momentum.